Claim 12.33. If alpha is in the interior of P of xy, then alpha is in the interior of P of xz for any z not equals to xy. Proof. Suppose alpha minus epsilon is in P of xy for some epsilon greater than z arrow. By neutrality, we have that epsilon over 4 minus epsilon over 8 equals to epsilon over 8 is in P of yz. By claim 12.32, we now get that alpha minus epsilon over 4 is in P of xz, which implies that alpha is in the interior of P of xz. By similar arguments, we also have that if alpha is in the interior of P of xz, then alpha is in the interior of P of wz. Thus, we get that for any x, y, w, z in A, not necessarily distinct, the interior of P of xy is equal to the interior of P of wz. Denote the interior of P of xy as P. Claim 12.34. P is convex. Proof. We show that alpha beta in P implies that alpha plus beta over 2 is in P. A known fact from convexity theory then implies that P is convex. By claim 12.32, alpha plus beta is in P. We show that for any alpha in P, we have that alpha over 2 is in P as well, which then implies the claim. Suppose by contradiction that alpha over 2 is not in P. Thus, by claim 12.31, minus alpha over 2 is in P. Then alpha over 2 is equals to alpha plus minus alpha over 2 in P, a contradiction. We now conclude the proof of theorem 12.26. Neutrality implies that zero arrow is on the boundary of any P of xy. Hence, it is not in P. Let P bar denote the closure of P. By the separation lemma, there exists a k in R to the n such that for any alpha in P bar, k times alpha is greater than or equal to 0. Suppose that f of v is equals to x for some little v in capital V and fix any y not equal to x. Thus, v of x minus v of y is in P of xy, and k times v of x minus v of y is greater than or equals to 0. Hence, k times v of x is greater than or equals to k times v of y, and the theorem follows. We have just seen a unique example demonstrating that there exists a domain for which fi maximizers are the only possibility. However, our natural focus is on restricted domains, as most of the computational models that we consider do have some structure, e.g. the two domains we have considered in this chapter. Unfortunately, clear-cut impossibilities for such domains are not known. Open question. Characterize the class of domains for which fi maximizer are the only implementable functions. Even this question does not capture the entire picture, as for example, it is known that there exists an implementable but not an fi maximizer CA. Nevertheless, there do seem to be some inherent difficulties in designing truthful and computationally efficient CAs. The less formal open question therefore searches for the fundamental issues that cause the clash. Obviously, they are related to the monotonicity conditions, but an exact quantification of this is still unknown.